So in this video, we're going to take a look at what is technically 4 theorems, but it really comes down to 2 main ideas. Let's jump in and take a look at the first one. It's called the perpendicular bisector theorem. And what it says is this: if a point is on the perpendicular bisector of a segment, the perpendicular bisector of a segment, then it is, and then I'll fill that in a second. But let's first just take a look at the hypothesis of this theorem, the if part, and remind ourselves what it means to be on the perpendicular bisector of a segment. So if I look over at this picture here, I notice that I have segment XY, and then I have this line L that's coming down through here, and it's doing 2 things to segment XY. It is making a 90-degree angle with the segment, so it is perpendicular to it. And it is cutting that segment into 2 equal parts, segment XQ and segment YQ, that are congruent to each other. So that is the perpendicular bisector of segment XY. It's perpendicular to it and it's bisecting it. So if I look at point P here, it's on that perpendicular bisector, right? So point P would be a point that we're talking about, right? Point P in this diagram over here is the point that's on the perpendicular bisector. Then the conclusion would be that point P is equidistant from the endpoints of the segment. From the endpoints of the segment. So what does that mean? Well, if I have this picture over here, point P on the perpendicular bisector of segment XY, then P is equidistant from X and Y. Equidistant means it would be the same distance from P to X as P to Y. So I could mark on my picture that segment PX would have to be congruent to segment PY. And that's what the perpendicular bisector theorem says. If you're looking at a point that is on the perpendicular bisector of a segment, that point will be the same distance away from one endpoint of the segment as from the other endpoint of the segment. So how can we prove that this must be true? If I look up here, if I gave you, again, the information that I gave you at the start of that problem, how do you know that from P to X has to be the same distance from P to Y? How can we prove it? Every theorem can theoretically be proven to be true. Well, if we go back, I'm going to erase these marks that I put on here. If I go back to having this information about my diagram, and I look at this diagram as showing me 2 triangles. If I look at triangle PQX right here, triangle PQX, and then I look at triangle PQY right here, I might notice something interesting about those triangles. I would notice that they have a pair of congruent sides. Segment XQ is congruent to segment YQ. I would notice that they share segment PQ, so it would be congruent to itself. And I would notice that if this is a right angle, this is a right angle. So angle PQX would be congruent to angle PQY. Well, that's a pair of sides, that's a pair of sides, that's a pair of angles that is included between these sides. So what this all tells me is that triangle PQX is congruent to triangle PQY by side, angle, side. And now if these 2 triangles are congruent to each other, then that would imply that segment PX is congruent to segment PY by CPCTC. And that would be true no matter where we put point P, right? If we moved point P, or if we picked maybe a new point that maybe is called point, maybe this is point P1 and this is point P2. So it's just like a new location for point P. Now, this distance from P2 to X would still be congruent to this distance from P2 to Y, because these 2 triangles would now be congruent for the same reasoning that I used down here, right? So that will always be true no matter where I locate that point on that perpendicular bisector. So that's called the perpendicular bisector theorem. Now, there is the converse of the perpendicular bisector theorem that also ends up being true. The converse, remember, is where we take the if part and the then part and we switch it around. So this would now say if a point is equidistant, let me change that to a different color so it's easier to read. If a point is equidistant from the endpoints of a segment, so in other words, if I look at this picture here and I see that point P to X is the same distance as point P to Y here, that's the situation we're describing in the hypothesis, then that point is on the perpendicular bisector. It's on the perpendicular bisector of the segment. Right? So point P must be on the perpendicular bisector. So now there's lots of points, there's lots of lines that point P could be on, right? There's an infinite number of lines technically that point P could be on. You could draw an infinite number of lines going through point P. But here I see one line L, right? It goes down here and it intersects the segment at Q. What this perpendicular bisector theorem would tell me is two things. First of all, if I knew that that Q was the midpoint of the segment, in other words, if I knew that these two parts were congruent, then I would know that these angles have to be right angles, right? Because if these are congruent, then it's on the bisector of the segment, which would mean it's also going to be the perpendicular bisector. Or we could say, if I knew that this was a right angle, then I know that this is on a segment that's perpendicular to segment XY. It would also be bisecting it, would be what I would be able to conclude. This one's maybe a little bit trickier to apply. We got to know, first of all, that P is equidistant from X and Y. And we got to know either that it's on a line that's bisecting the segment, allowing us to say that that line would also be perpendicular to segment XY. Or if it's perpendicular to segment XY, this line that point P is on, then that line would also be bisecting segment XY. So the way we're going to state that is we're going to say that line PQ is perpendicular to segment XY, and then XQ would be congruent to QY. Right? So that's the converse of the perpendicular bisector theorem. Then we're going to look at something called the angle bisector theorem. Right? The angle bisector theorem. And it says if a point is on the bisector of an angle, then something special happens. I'll get to that in a second. Just look at the situation that's being described by this hypothesis. My point D is what I'm talking about. So point D is the one where we'd be kind of looking at over here in this diagram. You can see that it is on this ray AD, right? Point D is a point that's on ray AD. And ray AD has taken angle BAC and it's divided it into these two congruent parts. So it has bisected angle BAC. So I'm going to kind of say this is the bisector of angle BAD. It is the bisector of angle BAD. This theorem now tells us that that point will be equidistant from the sides of the angle. And the angle, we can say in parentheses, that got bisected. That was bisected. So what does that imply for our picture here? Point D is now equidistant from the sides of angle BAC. Oh, I wrote BAD there. Let me just fix that real quick. I know some of you guys might have been confused a minute ago. That's supposed to be a C there. It is the bisector of angle BAC. So what does this imply here? Well, if I notice this segment that goes from D to B, it's a segment that is perpendicular to the side of angle BAC over here. And then I have segment DC that's perpendicular to the other side. Anytime we want to measure the distance from a point to a line or a ray or a segment, right? If I want to measure the distance from a point to a line, ray, or segment, I don't want to measure that distance kind of going at an angle, right? If I drew in a segment, I'll just draw a segment. If I drew a segment from D over to this ray that way, or a segment from D over to this ray that way, that would not necessarily represent the distance that D is from that segment. Because when I say the distance from a point to a segment or a line or a ray, I want to know what is the shortest possible distance over to that object from that point. And if I'm trying to go the shortest distance from a point to a line, a ray, or a segment, I'm going to go, most people say, straight over to it, which is implying I'm going to go over along a path that's perpendicular to that object, right? So the shortest way to get from D to this ray would be to go along this path that's perpendicular. It wouldn't be to go along either of these paths that are not making a 90-degree angle with that ray. So those two segments are representing the I erased part of my diagram here. Let me put that back in there. Those two segments are representing the distance from D to each side of that angle. According to this theorem, those two segments should be congruent to each other. They should be congruent. Now, I might want to think for a second how that would be true. How would I know that in this diagram, segment DB would have to be congruent to segment DC? Well, it's similar to the way we knew that the perpendicular bisector theorem would be congruent. If I look at this picture, the way, with what the information was that I had earlier, I had that this angle here was congruent to that angle. This angle would have to be congruent to that angle. So that's two pairs of angles between these two triangles. And of course, they share segment AD, so that would be a congruent pair of sides. So I would be able to look at that picture and I would say, oh, triangle BAD in that picture is congruent to triangle CAD by angle, angle, side. And if that is true, then it implies that segment DB would be congruent to segment DC by CPCTC. And that's how we know the angle bisector theorem works. Now, just like the perpendicular bisector theorem, there is also a converse to this theorem that is true. The converse says if a point is equidistant from the sides of an angle, so I look here and I notice, hey, look, here's point D. If I go from D over to ray AB along a path that's perpendicular, right? So I'm going, if you want to think of it as straight over to that side, and I'm going straight over to the other side along this path here, segment DC, those two paths are the same distance. So D is equidistant from this side of angle BAC and this side of angle BAC. It's equidistant from the two sides of angle BAC. Then we know it is on the angle bisector, or on the bisector of the angle. The angle bisector of the angle. That's a little repetitive, but you get the idea. You could probably just say it's on the bisector of the angle. So in this picture I see here, I'm like, okay, this point D must be on the bisector of angle BAC. Well, it's on this ray here that goes from A through D. So in this picture, I must be able to say that this angle is congruent to this angle here. Angle BAD must be congruent to angle CAD. And again, the reason I would know that is because these two triangles now would have to be congruent by HL. They're both right triangles. They share the hypotenuse, segment AD. Their legs are congruent here, segment DB and segment DC. So I know that triangle BAD is congruent to triangle CAD by HL, which would imply that angle BAD must be congruent to angle CAD by CPCTC. That's how we know this theorem is true. So we have, it's technically 4 theorems in this section, but you can see it's really just 2 with the converse of each one. We had the perpendicular bisector theorem. Let me just scroll up and see that. When a point is on the perpendicular bisector of a segment, it's going to be equidistant from its endpoints. And we had the angle bisector theorem, which says if a point is on the bisector of an angle, it's going to be equidistant from the sides of the angle. And then we had the converses of both those theorems.